Okay, great. So sorry for the delay. Let's start. This is where I ended last time, talking about some alternatives to grouping technique. And just remind you, the whole point of the last lecture was we finished the gradients for the energy, and we were looking at how to actually measure the expectation value of the Hamiltonian with a constructed wave function or any other operator, because in case of gradients, let's say we may want to maybe do not the Hamiltonian, but rather Hamiltonian commutator with some generator. That is possibility too in the case of adapt VQE, right? So generally some normal operator, meaning that something that can have eigenvalues when we can diagonalize. All right. Okay, so we looked at the various ways of doing that. Mostly the main restriction is that if we are dealing with the Hermitian operator, in order to measure it, we need to sort of present it in the form where it's some sort of a polynomial of the z operators, right? And obtaining this form is not straightforward. It's equivalent to diagonalization, and therefore we were talking diagonalization of H. We were talking about the simpler version where we partition H to fragments and then diagonalize fragments separately, right? Or this classical shadow tomography technique, which I mentioned at the last point, was just effectively using the unitaries that from a random set, and it is a different view on the measurement problem. Instead of starting with the fragments, which can be diagonalized, just put the unitaries on the Hamiltonian and see what you can measure, right? So presumably the idea is that some of this in some whatever unitary you put, the Hamiltonian will have in the qubit representation some parts, some linear combination of Paulis that are fully, these Paulis are fully Z operators, right? So these are products of ZIs and a product of ZIs. And there will be also, of course, part that is not something of this type. It will, these Pauli products will have x's and y's, and on a product state that you will get after the collapse of the wave function, you simply will have an expectation value of this part to be 0, right? So you won't learn much about this part. You only learn about this part that we call Ising part. Right, so like there, OZs, that's the Ising part, and not OZs, that's the part that we getting a 0 expectation value for. And the reason, essentially, in this picture, we're getting the 0 expectation value for this is because when you do the measurement, you project to the product state, and any product state on Pauli products that containing X or Y, that will be just 0. Okay, so that's the kind of the idea. So then if you do cast this unitaries from a random set, there could be parts that you learn a lot. Like with some unitaries, there will be a large Ising parts and you learn a lot. And with some unitaries, there will be small Ising parts and you don't learn much. All right, and that's the problem with the just completely random selection of unitaries. therefore, in the literature, there are these works that try to do some so-called de-randomization or biasing. And the idea is very simple. You want not completely random unitaries that you can do, but instead you want unitaries that produce larger Ising part, right? So that you learn something. But this is very similar to the approach where you start with the Hamiltonian and you see, okay, which fragments you can separate with what unitaries will you diagonalize them. And so the two approaches really kind of come together in that view that they want this diagonal part to be large, and that diagonal part is nothing but the Ising part, really, because in order to be diagonal, it's a sum of it's actually some products of these, right? Okay, so these are the works. I'm not going to go over like all of them. Just will show that essentially we show results essentially which methods win and what is important for reducing the number of measurements. Also, interestingly, the two sort of views of the same problem inspired when the shadow tomography came into life. Was published, I guess, where is it? A previous slide. I think it was 2020, and it sort of inspired us thinking about the fact that we could maybe benefit from essentially learning about some parts of the Hamiltonian from multiple fragments. Okay, so that was the idea that was inspired by the shadow tomography, because in this view, when you just put the unitary and then do the measurement, technically, if one unitary U1 allows you to say measure like some part of the Hamiltonian, that becomes Ising, and then there is another unitary that allows you to measure another part of the Hamiltonian. Let's say this is the kind of roughly speaking the Hamiltonian that we're trying to measure its parts. Then there could be unitaries that effectively get us information about parts that were measured in the previous frames, right? And so you can benefit from that by combining the information from different frames. That's what then we start essentially doing by thinking about effectively optimizing the fragments with and getting the lower variances. That could be related to this general idea of getting more information from the parts that sort of overlap, that are Ising in several frames. Okay, yeah. So,
but do you then not measure stuff like twice?
You do. Yeah, you do. You do measure some. Let's say the simplest example would be, let's say if we do some Clifford transformations, n-body and qubit Clifford transformations, then some Paulis you could cast into the Z's in different frames, and effectively you can estimate them more accurately. Okay, those Paulis, and overall that reduces the budget of the number of measurements because they appear in multiple frames. Okay.
But you must know that. Like if
yeah.
you don't know it, you accidentally measure stuff twice.
Right. You must know the overlaps, and you must account for that. Right. And yeah, I guess that is related to some method that was I didn't talk about this in details, but it's called measurement allocation, and then it was superseded by the method that was even more efficient, as we learned as coefficient splitting between it's actually the coefficient splitting I was talking already about. It's if you have a situation like this, that's I guess a good example that in one frame, you could learn this. In another frame, you could learn this. And this guy, you could kind of learn about it in 2 frames. You could either allocate measurements accordingly, or you could just split the coefficient into, like, let's say the coefficient of this term in Hamiltonian is C. Then you could make it minus alpha and alpha into groups and optimize alpha to reduce the variance and reduce overall the number of times you do the measurement. Okay, this is the type of plots we analyzed usually for, let's say, molecules, small molecules. It's like I think largest one is here, I believe 16 qubits. It's on a minimal basis. And what we have, a histogram of essentially for the measurement numbers in millions, right? It's on the y-axis. In order to achieve the error, which is millihartry, chemical accuracy error, a little bit more stringent actually. It's like 1 kcal per mole, I believe it's 1.6 millihartry. And then this one is just a millihartry. So this is 1. And this one is millihartry. Okay, so what do we have here? So we have various methods. The grouping methods are last 3. So it's coefficient splitting, measurement allocation, and simply just greedy search of groups. And the groups here first considered are qubit-wise commuting groups. So we split the Hamiltonian into fragments that are qubit-wise commuting. So remind you, the example of qubit-wise commuting would be, let's say, x1 plus x1 z2 plus maybe z2, right? So something like that. So where we have commutation along each qubit. So there are small groups, but in order to measure them, you only need to do a single qubit Clifford transformations, which are the cheapest Clifford transformations. And therefore, people like using the QWC because it doesn't require you to introduce the gates that need like non-local interaction between different qubits. And that is kind of better for because the non-local Clifford transformations, they involve more they introduce with a higher rate the error. Okay. Plus, in the current devices, not everything is fully connected. Therefore, there is yet another overhead if you have connecting the essentially unitaries that need to connect multiple qubits which are far away from each other, maybe on the hardware. Okay, so going back to the plot, so the last 2 columns here in each molecule is this one is overlapping group of, so essentially this is a variance of the shadow tomography, de-randomized one, and as you can see, the general message here is that grouping techniques are doing much better than the shadow tomography. Here, in order to put everything in the same plot, I needed to scale up hydrogen and these 2 molecules 110 times, but the picture is more or less the same. And the one thing that I want to just say here, if you could see in the literature, sometimes the claims that these shadow tomography techniques are better than the grouping, it's because the story goes like this. So when we were doing the grouping, there are multiple ways, of course, to do grouping, and solving this kind of minimal click cover problem. And initially, we were not, I guess, that knowledgeable of the statistics. We were just thinking about the number of groups. Okay, And of course, you could break down the graph to make sure that the number of fully connected pieces is the lowest. And this is what LF stands for. That's a kind of one algorithm to reduce the number of groups in general. And that was optimal, of course, for if you want to reduce the number of groups, but that doesn't really matter for the number of measurements that much, because you could have a simple example where, okay, the Hamiltonian could be split either in 2 Hamiltonians or 100 Hamiltonians. And in case of 100, it could be better than in case of 2. Why is that? Of course, the fragments will be different in 2 cases. But the problem is that with 2, if the variances of these 2 fragments are large, then you're going to get a lot of measurements to do in order to achieve the high accuracy. While with the hundreds of fragments, if the variances are very small, then you end up with a better measurement requirements, right? So later we realized that the greedy algorithms indeed are way better in reducing the number of measurements. And but in the original paper, we were kind of thinking about more like reducing the number of fragments. And so then all these subsequent works, they like to compare things with our results with the lower number of fragments and the suboptimal in terms of number of measurements. But if you just look at the sort of greedy algorithms versus the shadow tomography, you could see right away that still, well, greedy, even without any optimization of variance, the greedy algorithm is way better than all this classical shadow tomography, even with all the attempts to reduce the number of measurement by de-randomization. Yeah.
Do you have it with last first by any chance, the graph with LF?
With LF, I don't have a graph, but in this
that's what we are using. So.
Yeah, so classical shadow tomography people, they use that. So once we start focusing on the number of measurements, we actually never looked at the LF, because we realized in our internal kind of calculations, we realized, okay, well, greedy is a way to go, and LF is always going to be suboptimal, right? So
how does I reckon it's SI, whatever.
All right, sorted insertion. That's the name of the algorithm. Doesn't say much, but it's a greedy algorithm essentially.
How does that scale compared to LF? Classically.
Classically, I think it's even better because greedy is simpler, right? So that algorithm sorted insertion, what it does, if you have a Hamiltonian with a, of course, linear combination of Pauli products, it's based on the coefficients, organizes the Pauli products, let's say n to the 4th, P1 and so on, the n to the 4th, and then goes and tries to find for the P1, let's say some Pi that commutes with P1, right? And then the group will be P1 and Pi, and the closer Pi to the P1, the better, because the coefficients are organized. So this is the largest coefficient and this is the lowest coefficient. And so the group contains, it's a bigger group with, if you think about the size of the group based on one norm, which can be heuristically said that it defines the somewhat related to somewhat to the variance of the fragment that maximally can be obtained. All right. So, and then it tries to essentially go over the list and tries to put, if Pi is in the list, then it looks what else can be put in that list, and then Pj needs to now commute. If you want to add Pj into this group, Pj needs to commute with P1 and Pi. Of course, such greedy algorithm, as any greedy algorithm, has issues that. Maybe there is a Pj high in the list. If you didn't put Pi, then Pj could be put in this list, because Pj, say, commutes with P1, and then there may be Pj plus 1, which is really close to Pj. You could also put, but because you already put Pi, both of them needs to be selected lower in the list. So this is a typical problem of the greedy algorithm. So not saying that the SI is the most optimal, but it does the work quite well, and it's easy to implement classically.
So that it means it's basically tailored to a given fermionic operator, in this case, the Hamiltonian.
Yeah, in general.
So let's say I want to
yeah.
measure afterwards. I would also want to measure, I don't know, gradient or anything else.
Right.
Might be in the same group of Pauli's.
Mm-hmm.
The grouping I made based on Hamiltonian might not be the same optimal grouping that I would then use for the next fermionic operator that uses the same, that maybe use the same Pauli strings. So I wouldn't have to measure them again. But based on how I grouped them initially, based on the electronic Hamiltonian, they might not be optimal for the next property.
That is correct in general. The more, yes, and that's kind of is correct. If you have more operators, let's say the gradient case, right? So you have all these operators to measure, and technically they have maybe their own lists of Pauli's, right? Pauli 1 and then Pauli I, right? So based on the generator. So they have their own lists, and then finding the optimal set of Pauli's that could be measured together, and they will be optimal in terms of the variances of this. It's a complicated problem classically. And there, in this type of problems where you have a lot of operators to deal with, shadow tomography actually is getting better. We saw in some examples of the excited state problems where you go after excited states, and there are multiple states or different energy scales. There we need actually in excited states find the matrix elements of the Hamiltonian, say with some functions. So then if these functions are effectively, let's say, one unitary and various excitations, IA, let's say, on the particle determinant. So this, let's say, is the, say, this is phi A and JB, the A, something like this. So then turns out that shadow tomography is becoming better because it's really hard to tailor your grouping to multiple operators, which may want different things in terms of their variances, right? So yeah.
But that's why then something like LF. Do you know how LF would then? No.
No, we did. No, we didn't investigate LF. There is. I don't think big reasons to believe that it will be better because it doesn't know anything about the variances, right? So it's just a very heuristic kind of way of thinking about the problem is that the fewer the fragments, the better, but it doesn't account for any statistical error, right? So in that sense, it's as good as any other technique, but shadow tomography is sort of maybe just doesn't try to optimize much, but in general, it's actually getting more competitive with the more operators you need to measure. But once you have a clear one operator to measure, then you could definitely optimize it in terms of grouping the terms that have lowest variance. All right. Now, if we go to the fully commuting techniques where we don't anymore constrain ourselves to unitaries that need to be a single qubit unitaries. There, for comparison, I don't have any shadow tomography techniques, but the coefficient splitting, the best approach from the previous plot in red, and then fully commuting, as you could see, is way better, but they will require the transformations that involve more than a single qubit, right? And again, the same picture, the greedy, here I don't have a left, but the greedy, and then you could improve it even further by doing all this sort of coefficient splitting, the one that I was explaining there. Because this case is indeed the fully commuting case, where Z1, Z2 commutes with X1, X2, not qubit wise. but fully. And yeah, so this essentially another message you could get out of this is by looking at what the, I guess, for the biggest system, how many millions of measurements you need to do. And here it's less than, becomes close to probably 3-4 millions for ammonia. And in order to optimize the coefficient splitting, we use variances that are coming from CISD wave function. As don't forget, for the variance of any fragment, right? So this, what we mean by variance is we have HN square minus the expectation value squared, right? So this is the quantity. And then if you don't have a wave function, then you cannot calculate that quantity. So for optimization purpose, we of course don't use the wave function that is a full CI wave answer for this problem. And instead we're using the sort of the approximation, which is a single and double CI. And of course, if you go into strongly correlated regimes, this function becomes somewhat less optimal. And I guess in general, one would wanna maybe do some sort of a hybrid Bayesian approach where you maybe start with approximate wave function, but when you do the measurements, eventually you get the sense of what the variance is for the fragment and maybe re-optimize. So that just makes the whole thing more complicated. We haven't done that, but that probably statistically is more sound way of going and improving the wave function that we used for the estimating variance. And all these estimations, I just needed to figure out what fragments are the best.
But it doesn't mean the CISD wave function is totally classically done.
Yeah, that's right. Yeah, because
I don't know if it works, but what would happen if you use the actual wave function but just Clifford it?
That we
Or does
haven't,
it not
yeah,
work with
that
variances?
we haven't tried. What you're suggesting is
Substituting
Clifford
everything with
transformation.
No, by
Clifford,
substituting everything to make the whole circuit full Clifford, so you can simulate it classically very well. And then
right.
classically
So
simulating the variances based on a Clifford version of your answers.
but essentially, if you have a full CI wave function, you want to approximate it, right, with the Clifford transformation applied to the, let's say, Hartree-Fock state.
I mean, like when people do error mitigation, where they do Clifford regression.
Clifford what? Rotation?
In error mitigation,
Yeah.
sometimes you do Clifford regressions. So they have their actual answers.
Right. And
But
then
they substitute all the parameters by just Clifford gates, X, Y, Z, C control X. Because then you can very easily simulate even large circuits classically.
right.
Could you use that to classically simulate the variances of a fully Clifford version of the actual?
I
answer?
see the issue with this technique is that in real situations, we don't know this, right? To even start thinking about the Clifford approximation to it.
But you,
So CISD,
you set up an ansatz, no?
we set up ansatz in VQE, you mean?
Yes.
I see. I
So
see.
using
Okay, so then here, let's say we do VQE, which we know only in terms of the generators, right? So we know this guys. They apply to say Hartree-Fock,
Yeah.
right? So we know these guys, and we could obtain now some sort of a Clifford approximation based on the generators, and maybe throwing out some of them, some of the things that are far from Clifford, and the substituting of Clifford. Sure, we can try doing that. That is a possibility. We haven't done it. We were doing just approximate classical. Classically also sort of efficient, but what you're suggesting is, I guess, more quantum computing a version of classically efficient ansatz. Yeah, could be tried. Yeah, but I feel like it also would be nice to have a adaptive scheme where whatever this initial wave function suggests in terms of variances, you could kind of improve that because you eventually gather the results of actual measurements, right? So you could estimate, you could improve your prior of the variances with the new results. Okay, so with that, right, so this advantage actually survives lower fidelities of non-local transformations. What this means is that if you account for the reduction of the variances and you also put into consideration the fact that because you put non-local transformations, the fidelities well, kind of reduces the advantages. So as we've shown in that work 2022, for most system advantages sort of survive, even if you account for the noise coming from the non-local gates. Okay. All right. So now another comparison we made for these small systems is the. Okay, so we have lots of techniques in the qubit space and fermionic space. Which ones eventually is the way to go? Which ones are better? And you could see red and green, the greedy fermionic and qubit techniques. By qubit, I mean the fully commuting techniques. And generally, fermionics are better, but in some cases they are not, right? So. Yeah, so that's kind of a mixed message here. But what is clear is that if you start putting this optimization with the coefficient splitting of fluid fermionic fragments, those are the orange and blue. Correspondingly, orange is for fermionic and blue are for the qubit. So then you, of course, reduce the variances, and this is the way to go if you want to really reduce the number of measurements. Again, the situation could be that sometimes fermionic a little bit better, this case, and sometimes qubits are somewhat better. So that it's a little bit, depends on the case, right? But what is clear is in all these techniques, if you could do optimization of variance, that gives a big impact. Okay, that's what you want to do, and as we will see. Beyond grouping, of course, there are some other ways of doing the measurement. It's an interesting area. How else can you measure on a quantum computer? But some of these more sophisticated schemes, not always obvious how to optimize variances in them. And if you don't have a really easy way to optimize variances, then it becomes difficult to make it competitive with this measurement techniques based on the grouping, where optimizing variances is straightforward. Okay, and what are the things to take from here? Yeah, generally fermionics are better, but qubit-based schemes are a little bit faster because well, they are easier sometimes to optimize with all the variances and all the partitioning. Now, I guess one thing to also get out of this is that if we compare, if this is like ideal case scenario with no noise yet, we could do ammonia now within the less than, I think, 1 million of less than 1 million measurements. Then if you compare that with some early results, like in 2017 IBM paper, that was the first VQE experiment for ammonia. They didn't do ammonia there, but if you look at the variances and stuff, so then with their qubit-wise commuting approach there, it would be 500 million. So we made like a 500 x speed up on the measurement front. And to give you an idea of what does that mean in the actual timing, and that's again a little bit on a more optimistic side. So 1 million of measurements on the superconducting architectures could be within 1 minute. Probably it's more like 10 minutes because of if you wanna especially within those 1 million switch between different frames. The actual gates are very quick. They are, as I was told, like a nanosecond time scale. And but after doing the measurement and you need to wait and reset the device, there is this microsecond reset time that they need, and that is the main bottleneck. Microsecond means essentially you get 10 to the minus 6 for one measurement at least, and that's why it's slowing. But on the ion trap devices, the numbers are much worse, and usually 1 million measurements on the ion trap, it's like you cannot do these days. It will require a week or so to do that, right? So it's for superconducting machines like IBM mostly, or Google, but IBM is what people mostly use, right? So, and that is only for if you set up the circuit and do the measurements for Hamiltonian and minimal basis. Still, like systems like of this size, of course, you could do the entire calculation on your laptop faster than 1 minute. But this is the situation right now. Okay. Oops. All right. So, what are the other alternatives? I wanted to chat a little bit about alternatives of a grouping technique. And before I guess we get there, let's do our quick break, and then we'll reconvene with alternatives.
Okay.
Okay. Right. So we go with this alternative to the measurement grouping that I was presenting. And so the alternative essentially is called Adamar test. And the idea of the Adamar test is that it is like generally not only useful for the measurement, but as you will see for the fault-tolerant quantum computing, this circuit motif will be appearing as well. So that's why it's important to consider it, so that you are more or less familiar with what that fragment generally produces. Okay. Now, what's happening here is that we assuming that we know how to partition our Hamiltonian as a linear combination of some unitary operators, UN, right? And well, if you're wondering how this can be done, well, simply any Pauli product is unitary, right? Because Pauli product is 1 and it's Hermitian, so it's unitary. So then naturally, if you go to the qubits, you can use Pauli products if you want. But there are better ways to do this linear combination of unitaries. And then what does a circuit do is you create Ancilla qubit and you have your wave function on the target line. This is just to say that this is an n qubit line, and this one is 1 qubit line. And then what we do Adamar test. Oh, sorry, not Adamar test, but Adamar. We do Adamar gate, which I explain in a moment, and then UN, then H again, and we do measurement of the ancilla qubit, which will give us 0, 1 or plus. Sometimes we use 0, 1. Sometimes this is essentially equivalent to measure Z's plus minus 1. Let's see how it works. So initially, our function is just a tensor product of target wave function that we want to measure and ancilla. Then we do Adamar gate. Adamar is 1 square root of 2. It's a single qubit Clifford transformation written like this. And you could think of it, it as like essentially sigma z plus sigma x divided by square root of 2. Right, so unitary obtained out of summing two different unitaries. And okay, so what it does essentially it acts on the ancilla, right? And if we think of what happened to our initial wave function, it will turn into the function that is still tensor product, but now ancilla qubit will have instead of being 0, we'll have plus. So what plus means is just x or sigma x eigenvalue with plus 1. That's why it's called plus. With plus 1 eigenvalue, right? So how do we get the plus here? It's simply, if you think about what 0 is, well, 0 state is 1, 0, right? And in the notation, essentially in the basis of 0 and 1, right? So it's 1, 0. And then if we apply Adamar to 0 state, then this is just the matrix algebra. We get 1, 1, 1 minus 1, 1, 0. This is giving us 1 square root of 2, 1, 1, which corresponds to 0 plus 1 divided by square root of 2. This state is what we call plus state, because if you apply x, then you could see that x will give you plus 1 eigenvalue. We could simply do that. And what else? Well, there is if there is a plus, there is also a minus. There is a minus state where here we have just minus, right? And in the not to confuse, in this case we get plus. All right. Okay, then we are getting, this is function number 1, I guess, this function number 2, and then we are using this funny looking transformation, which is called controlled unitary, and we get in function number 3. So what is this controlled unitary? Controlled unitary is essentially unitary that acts the following way. Let's put it's the unitary that could be written as a projector, essentially as a unitary on the let's say target state yeah, so we have UN. This is controlled U, right? So the one that with the funny dot and UN. So this is a transformation that involves both ancilla and the target qubits, right? So what it is, it's the tensor product of two operations. One is we have act with unitary, but only if, let's say, we have, let's say, one state, one on ancilla, right? And we have identity if we have 0 on ancilla, right? So it's ancilla, and this is a target. So this is a controlled unitary, so it acts this way as a tensor product. And this is the projector to the one state. Okay, let's make P1. This is projector to the 0 state. So they are orthogonal. P1 times P0 is 0, and P1 plus P0 is 1. Okay, so what this thing does, it's a kind of even maybe an example of more general construction that one can use in general, that you can construct the unitary, bigger unitary, you extend it as a linear combination of unitaries in one space with the tensor product of here we use P again for projectors, not for Pauli products. Somehow we need to maybe separate that. Let me try to write the projectors more. Curly P. All right, so this is a general construction that you can see that if these projectors, they are orthogonal and form the complete set. So then you could sum unitaries multiplied by these projectors, okay, and you get unitary. And then this is one condition, and another condition is that these projectors sum to identity. Okay, and then from this you could see that if you take the extended unitary dagger, it will be identity on ancilla and identity on the target state, right? So it will be total identity. And this is one example of this happening. Now let's see how it acts on the state that we produced, right? So if we do controlled unitary acting on the state psi plus, right? So then plus state is, as we were discussing, a superposition state of 0 plus 1 divided by square root of 2, right? And so you could clearly see that this component, this part, will not be, there will be no action, right? And for this part, there will be this unitary, but this unitary will act not on the ancilla, but on the target state, right? That's kind of the idea. And what we get is a linear combination of unitary acting on the psi multiplied by 1 plus the same psi, and then with the tensor product of 0 with this 1 over square root of 2. So this is our state number 3. And what is interesting about this state is it's entangled state, right? So it's it was product state before, even though it was a superposition. That was a product state because the target and ancilla they form a product. Here with this controlled, unitary, we introduce entanglement, right? So depending on if it's 1 or 0, we have different functions on the target. Okay. So far clear here, right? So okay, great. So then what happens next? Next we have Adamar, another Adamar. So we apply Adamar on, sorry for the confusing notation because this is not Hamiltonian. Adamar, it's like not always we'll use H. Okay, so what Adamar will do, we know that Adamar in terms of the matrix representation, and to make it shorter, what one can easily see that Adamar acting on, it will be acting only on ancilla. Adamar acting on 1 will give us minus, and Adamar acting on 0 will give us plus, as we already seen this. And this is easy to see. If 1 will be here, not there, then you get 1 minus 1, right? Clearly. All right, so then we could write what the result will be. So we have un psi, and now 1 switches to minus, plus we have psi with 0 switching to plus, right? And we still have 1 over square root of 2 normalization. Okay, so this is our function 4 just before the measurement. That's function 4 for the measurement. Now let's write it down in terms of kind of still 0 and 1, because what we measure is z operator on ancilla, and we will be able to see what is the probability. The way I'm going with this is that I want to see what is the probability of measuring 0 or 1 for this wave function, and it will be clear that the probabilities of getting 0 or 1 will correspond to essentially expectation value of psi with UN operator magically. So in other words, we are encoding our expectation value because we are measuring the unitary operator, the expectation value modulus 1, right? So we're encoding that expectation value in the probability of getting some result instead of result itself, right? Okay, so this written in terms of zeros and ones will be, let's see, u and psi having 0 minus 1 plus psi plus 1 and here it's 1/2. And now we can collect the terms. That will be for 0. We'll get yes, divided by 2. We'll get u and psi plus psi, and then for 1 divided by 2, we'll get minus un psi plus psi. Okay. So this is our function before the measurement, and if we do the measurement, the probability of getting 0 or plus 1, probability of that will be simply absolute value with 1 essentially will be a norm of this component, right? So it's 1/4 of psi plus don't need absolute value here, psi, and then we have psi un dagger un psi, those are diagonal form terms, and then we'll have off diagonal terms, psi un psi plus Fermionic conjugate version of this, which let me write down explicitly, psi un dagger psi. So from here, this is 1, this is 1 as well, and this is something that we're looking for, right? So this is 2 real parts of psi un psi, and then probability 1/4, 2, or 1 plus 1 is 2, so it becomes 1/2. Here is 1 plus real part of psi un psi. Right, so that's the value. Okay, so probability for 1 for 0 and probability for 1 will be just with minus un, so that will be 1/2 1 minus real part of psi un psi. So those are the two probabilities, and you can see that we can extract a real part of our un. Now, 2 points. If there is a real, then in order to obtain the expectation value, you also want to find the imaginary. There is a way to do it, and it's not that difficult. I'll show like all you need for that imaginary to get, instead of real imaginary part, all you need is modify the circuit and get the so-called phase before doing this un. I'll explain what S is. Other than that, the circuit is the same with the same measurement, right? Okay, so this is the modification essentially. This just S, and the S is another Clifford gate, which is 1 I00, right? So this is a Clifford gate. And I guess the maybe we already have seen all the components of the Clifford set. Maybe it's a good time to demystify a little bit this notion. So in quantum computing, there is this a special group. It's called Clifford group. Clifford group. And what is special about it? It's okay. So there are multiple things which are special about it. One is that if you have a Pauli product and you use unitary from the Clifford group, then it will transform into another Pauli product. Okay. So that's what Clifford group unitary is doing. And interestingly, the Clifford group unitaries, they have a very small set of generators, meaning that if you make all the products of those generators, you get all the possible Clifford unitaries in the group. And the generators are the following. So it's Adamar we saw, S that we saw, and C naught. Right. So C naught is analog of the controlled unitary that we had, with the only difference it's very simple. It's C naught involves instead of this complicated unitary that was acting on the entire wave function and target space, C naught would be just sigma x acting if the if the projector onto the first here we have a projector on the state 1 of the first qubit plus here identity. It's the same projector on the 0 state. So this is the C naught because it's only essentially involving 2 qubits. That's the only 2 qubit gate. And then the matrix, there is an easy matrix representation, which if it's 2 qubit gates, then we could write it in a space of 4 states, 0, 0, 0, 0, 1, 1, 0, and then 1, 1, right? So we do that. So then the matrix will be, if the first qubit is 0, that means we're in this space. So then the second qubit is, we're doing nothing, it's identity. And then if we have first qubit to be 1, then it's a sigma x, which we also know it's like this. The others are 0. Right, so this is our C naught in the matrix form. And these 3 generators, they actually, you could find, essentially generate a lot of possible products. And the group is actually quite large, exponentially large. But because of this property, that any Paulis will go to Pauli, then this group will produce what will it produce? It's actually is a nice group because any, let's say, Hamiltonian operator, which can be written as a polynomial number of Pauli operators, if you apply Clifford transformations, it will go into the same number of Paulis. Okay, so that is the nice part, because you won't make Hamiltonian larger if you apply this unitary from the Clifford set in terms of number of Pauli products. Okay, so this is a useful property. And what else do we know? So like Pauli products themselves, they are part of the Clifford group, because if you multiply any Pauli by other Paulis, you get Paulis back. But Clifford group, even on the generator, you could see that they are not single Paulis. As we saw, had Adamar, and well, there is an easy way to show that this is not Pauli itself, because well, the trace is 1 plus I, and the trace of every Pauli product is, as we know, 0, right? So the trace of S is not 0. Trace of C naught is not 0, so it's also not a single Pauli. As you could see, the generators of the Clifford group are not Paulis, but if you make enough products of this H, S, and C naughts, you will start getting Paulis, because the Paulis are parts of the Clifford group, right? And they form their own Pauli group, and it's a subgroup of Clifford. So Clifford is a bigger group. What else should you guys know about Clifford group? It is related to Clifford algebras. The relation is actually already straightforwardly written here. So because Pauli products, they are also generators of a Clifford algebra, sort of Clifford group can be thought as a group that when you apply it to the generators of Clifford algebra, it gives you back another generator of Clifford algebra, right? So it doesn't create a linear combination, because general unitary, if you apply it to Pauli, you could get linear combination of Paulis. Here you get just a single Pauli. Okay, that's nice for algebraic properties. Let me see what else. Okay, so one last thing. Yes, two last things related to the fact that this is not universal group, a universal unitary group, meaning that you won't be able to construct a general n-qubit unitary, a general from the SU 2 to the n. You won't be able to construct the general SU to the n unitary, even though, because this is 2 qubit and this is 1 qubit unitaries. So by making products, you could make n qubit unitaries. That's not a problem. But the issue is that they are not universal, and you need, in order to make a universal set, this is something that, yeah, yes. I'm not gonna show, but there's a proof of that. So all you need is the square root of s, so-called T gate, which has this form, which is 1, and here e to the I pi over 4, 0, 0. So that's the only extra transformation you need to add to this T. And then you get the universal set, which is nice. It's like the same universal set as we talked in the case of qubits. We could take a universal set as all the sigma cubes and the sigma cube prime, single qubit and 2 qubit products. So it turns out you could go even fewer than this. Sort of this is absolutely lowest, but then you need to repeat them, of course, for generating kind of universal or any unitary from the set from the SU to n. And there's a proof of that. It's called Solovey-Kitaev theorem. So Kitaev theorem, which I'm not gonna prove, but there is a proof out there. You need to combine T, S, H, and C naught. Okay. And then any transformation could be approximated arbitrarily accurately with this gates. Now, the last thing is the last thing here is that if we have only in our unitaries Clifford gates, there is another theorem. It's called Gottesman-Neal theorem. Gottesman-Neal theorem. That says that any calculation that can be done with a unitary that comes from the Clifford set, this classically can be done efficiently. And that is kind of intuitively clear to me because, well, you could apply unitary to the operators, and the operators written in the, like as linear combination of Paulis, essentially you don't really increase the complexity of the operator by doing that, right? So, but again, this is not a mathematical proof of this theorem. You could look it up. So again, I'm not gonna go into the prove that. Usually it's used in order to show that, okay, whatever complications or whatever complicated unitaries you get, if it's only from a Clifford set, then it can be all done sort of classically on a classical computer efficiently. It's just a matter of finding algorithm. And then I guess the last thing is that in error correction algorithms, all the error correction is actually quite easily done on the Clifford transformation. That's why when we go from the NISQ era, like when we go from the situations where we don't correct errors to the error corrected codes, then all the Clifford transformations are cheap. And what becomes a main figure of merit is actually the transformation, T transformation, because to correct T transformation, non-Clifford transformation, actually takes orders of magnitude more time, and therefore every complexity of every algorithm in a fault-tolerant considerations, they will count number of T gates. Now, for the NISQ, on the other hand, T is just a single qubit, H is single qubit, S is single qubit. The C naught is the 2-qubit transformation, and for the near term, without error correction, people count C naughts because C naughts introduce the larger error, right? So there's an interesting difference here. Okay. Any questions? Cool. So what did we achieve so far? We found the way to produce essentially expectation values as a part of the measurement, right? And that requires the unitaries and partitioning of our Hamiltonian in terms of unitaries. Okay, so one can ask, all right, so what's the number of measurements here, and how efficiently we can partition the Hamiltonian in terms of unitaries, and what else this can do? All right. Well, it turns out because we are measuring essentially a quantity with the variance that is given by, what's the variance? The variance here is relatively simple for these fragments. And to make it maybe a little bit simpler for the analysis, let me say one more thing, is that our Hamiltonian is usually, well, it is really has a time reversal symmetry, so it's real object, real operator. So we have Cn, Pn, so all these coefficients are real, and all the unitaries are real as well in the Hamiltonian, and that means there's just an even number of sigma y's usually. So in that case, well, there is no need for the imaginary part. Okay, so we only worry about the real part, and the real part is enough. Now, what this means is that actually UN squared is already identity, and the variance of UN part is then very simple quantity that we supposed to take the UN squared minus UN squared, right? So this part is 1, and this is something that is just related to the quantity that we're looking for, right? So the variance is 1 minus expectation value squared. And then because we have a linear combination of unitaries and we measure them independently, then the kind of the situation with the statistics, the number of measurements, is not that hard to estimate, which I will do in a moment. All right, so we have a linear combination of PNs, which are, well, in this case, let's say Cn unitaries, which are also Hermitian. Therefore, the usual consideration of the variance of estimator for the entire Hamiltonian will be variance of individual unitaries multiplied by Cn square divided by the number of measurements that we need to do for each fragment, right? So that's the usual formula. And then if we do the following, like substitution here, right? So we have 1 minus expectation value of un squared, Cn squared divided by mn, sum over n's. Okay, so then worst case scenario for us is when these variances are all 1, because this number is, let's say, positive, right, between 0 and 1. And so the worst case scenario is that all these numbers are the worst case. When all these UNs are 0, which simply means that our wave function is a equal superposition of +1 and -1 in this real unitary state or unitary operator, right? So then we're gonna get the sum over n, Cn squares divided by mn, right? So that's our variance of the estimator. And if we do optimal partitioning of mn's, then we know the formula. If you split the budget equal, like according to this worst case variances, then we'll get the square root of variances. In this case, it's the Cn square, so square roots will be Cn absolute value, right, and divided by m, right? So that is our variance, and it is actually quite easy to show that this is always bigger or equal than the largest eigenvalue of the Hamiltonian minus the lowest eigenvalue of the Hamiltonian divided by 2. So this is the kind of the worst case scenario with the optimal partitioning. You cannot beat this number, right? So I will show this because it will be useful for other things.
So you can connect it to condition number of matrices?
Sort of, but I wouldn't call it condition number because condition number is a ratio between the largest
Oh, yeah,
and,
right. Yes, sorry.
And
yeah.
smallest. But yeah, so it's related to the eigenvalues of the operators
To the variance.
and to the variance as well, right? So this is a good point.
We have not a lot of diagonal elements in the matrix. Essentially, the variance will be small.
Right. So that we could discuss this. There are two things to discuss essentially in this inequality. One is what is delta E over 2? How is it related to the variance? Okay, so one relation that I haven't seen anywhere discussed, actually, even though it's a simple relation. Let's say if you have a Hamiltonian, right, and it has a spectrum from like a minimum kind of eigenvalue to the I guess, yeah, it's a discrete spectrum to the maximum eigenvalue. And the question one can ask, this is spectrum of Hamiltonian, right? So the question one might ask, what's the maximum over all the wave functions, the variance of such objects, such Hamiltonian, right? So what is the maximum variance possible? Because everyone knows that the minimum variance is 0 for the eigenstate of the Hamiltonian. Well, what is the largest what is the largest variance for the operator? That's the question that I haven't seen anywhere discussed, but it has a nice simple answer. Anyone want to venture a guess?
Equal mixture of the max and the mean eigenstates.
Right. It's the max minus mean divided by 2, and because it's a variance, it should be squared, right? So this is the largest variance. And that quantity over there, delta E over 2, this is exactly what I meant by it, delta E over 2 squared. That's the maximum variance for the Hamiltonian. Well, the bad news here is that technically, because we're working in the second quantized form of H, right? So what this delta E over 2 is the largest eigenvalue in the Fock space, not in the Hilbert space of an electron system. It's a largest eigenvalue in general, and if you know that, okay, if we have orbitals, right? Some of them are occupied, some of them are occupied in the n electron system. So we know that well, physical orbitals, physical one electron states, they don't go above 0. Like that would be a continuous spectrum of flying away electron. But in the finite basis, we have some orbitals which are high in energy. And then if you allow yourself to construct the largest eigenvalue of the Hamiltonian that is in the Fock space with a finite basis, of course, you will populate this kind of crazily high values, right? And that, at least even at the Slater determinant level, that will give you pretty good estimate what the largest maximum eigenvalue could be. You just occupy everything that is positive in the orbital energy, and then the lowest one will be occupying everything that is low, like with negative orbital energies. That those are kind of the possible estimates for the max and mean, and they of course large, and it's inconvenient. Now one can modify the Hamiltonian in order to bring this essentially spectrum closer to the n electron states, which is another story, and we'll talk about that later. But this is about the delta E over 2.
So if it's a property of the Hamiltonian, it doesn't help if I solve it in a subspace.
It doesn't help, yeah. That's the issue, because
So the same problem doesn't matter when you got like through those subspace methods or anything else. It's still Hamiltonian related. So that's
it's Hamiltonian related, but it's also related to the decomposition of Hamiltonian in terms of unitaries. That's the issue, that Hamiltonian in the space you start considering it, it's the operator, yeah, that has the certain spectrum. And the unitaries, they are some operators that have always the limited spectrum between, if they're real, plus minus 1. So then the coefficients will need to compensate for that, and that's the price you're going to pay, right? So that's the unfortunate aspect of this decomposition, but there are some things you can do by changing the operator. We'll talk about that, I guess, later in discussing the fault tolerant techniques, which are based on the similar decompositions. Okay, but then there is another thing that is easy to prove, and I wanna show it before the end. Why one norm of the unitary is always larger than the spectral we call this quantity spectral range. Spectral range. There is another quantity that sometimes in operator theory people use, spectral gap. Spectral gap. Spectral gap is the difference between minimum and maximum. So let's say ground state, or really sometimes in the Fock space, minimum is not corresponding to ground state, and mean plus one. And so this is a spectral gap. By the way, if you think about it, with the large basis set, or the say case of oxygen, minimum energy in the Fock space is not going to be ground state of the neutral. It's rather going to be an ion, because electron affinity of the oxygen is positive. So positive would that means the oxygen would like to have one more electron. Yeah, so that's why minimum has to be carefully considered in the Fock space. All right, so with that, what do we want to say? All right, so how do we prove that sum over CNs is always larger or equal than the gap? Sorry, not the gap, but the spectral range. So one way to easily see that is you take out the trivial part of the Hamiltonian. So let's say Hamiltonian generally is not an operator which is traceless, or okay, the traceless, I guess, part not related here at all. Like, forget about it. All right, so just let's say we have a possibility for the shift that involves the identity operator, right? And then we have non-trivial part that we want to measure, because there is no point of measuring identity if we could easily ignore this part, because we know that what identity expectation value will be for the wave function, right? It's going to be one, because it's going to be psi identity psi, and that's one, right? So we know it. We don't need to measure it. So that's why we sort of remove this from the consideration right away, and we can write this like this. Right? This is an operator, and we have NCN UN. And then what one can do is simply consider spectral norm of left and right side. Right? Spectral norm means well, largest eigenvalues. Right? So H minus SI spectral norm equals, of course, spectral norm of sum CN UN. And here we could use triangle inequality with the spectral norms, or any norms really, that triangle meaning that the sum of two sides is always bigger than the one side. Doesn't matter how large the last side is, right? So that will mean that we have sum over Cn absolute value times the norm of UN, right? And so the norm of unitaries is 1. Therefore, this simplifies to be only the quantity we're interested in, this one, right? And it's larger or equal than, and then here there is a Hamiltonian with a arbitrary or potentially arbitrary shift, because we can shift anything. And the question here is, what's the one norm of H minus SI? We can make this as essentially this is the largest eigenvalue. So what this means is that, imagine if we have H, right, and this is the maximum, and this is the minimum, and there's somewhere 0, right, potentially. So and because it's a quantity largest by absolute value, so it's whichever is closest to farther away from 0, right? So in this case would be this, but if it's shifted, then it could be this. Depends on how far, like by absolute value, right? And then this shift is completely arbitrary. We could add any shift we want, and then there is a way to minimize this quantity by shifting sort of in a way that is symmetrical with respect to 0, like this, minus, plus, right? And well, this is still true. Therefore, the delta E over 2 will always be, this is minimize over shift. This one is always larger or equal than delta E over 2. Oh, in the minimum case, it's the same, but the true one will always be larger or equal. Okay, and so then we could see that this condition will always be satisfied, and one norm is restrained by the spectral range. Okay. All right. So for the last 10 minutes, let's see. Now, what would be possible alternatives to just doing very simple unitaries here, like Pauli products? Could we do something more sophisticated in order to use this scheme for more efficiently? And the answer is yes. We actually, turns out, we can represent any Hermitian operator like Hamiltonian with just 2 unitary transformations, right? So there is always a way to write this as a U plus with some coefficient plus U minus with some coefficient, right? Now, this U plus U minus, they are given by the following expressions. We take the Hamiltonian, we divide it by spectral norm plus minus I square root 1 minus H by spectral norm squared. Okay, so these unitaries and the coefficients C plus minus really is just they both absolute spectral norms of H divided by 2. Okay, so this you could see will always work simply because okay, so these are, first of all, one can show that these are unitaries. How do we show that? Well, U times U dagger, this would be 1. And what happens is, well, essentially either plus or minus, doesn't matter. So the U plus dagger is equal to U minus. And because this is what separates them, and conjugation sort of changes the sign, right? That means that U plus, let's say, dagger, U plus is equal to U minus U dagger, sorry, U minus U plus, and that needs to be identity, right? So this is easy to see by taking this, let's say, I'll call this small h, normalize h, right? So if I take this normalize h with minus I square root of 1 minus h square and multiply by the same with plus square root of 1 minus h square. Then opening the brackets will give me h square. Then another term will be plus 1 minus h square. And then there will be minus I h square root 1 minus h square plus I h square root 1 minus h square. These guys will be gone. This will cancel this, and then we don't have one left. Right? So that's how we show that this is indeed unitary. Okay, and the only problem with this unitary is that it is hard to implement, right? Otherwise, it's perfect. The square root of operator that is with unknown spectrum and hard to diagonalize, that is not easy to construct, right? Other than that, it's perfect. So we cannot use that, but it would be nice. Instead, what we can do is we can group some of the terms, like let's say if we think about the Pauli products, right, as our the most or the simplest unitaries that we can use, then what we can do, we can group some of them together and obtain simpler unitaries. Sorry, bigger unitaries, but with turns out with the one norm, which is gonna be better in terms of being smaller, right? So how do we group unitaries? So Pauli products are unitaries, but if you add two together, then generally they are not anymore like Pauli product, or they are not unitary transformations, right? So, but there is a way, and we saw it already in Adamar. We saw that sigma x plus sigma z divided by square root of 2, that is Adamar, which is unitary. And what's happening here, why one Pauli, another Pauli normalized, as we could see, gives us unitary, it's because of this magical relation where if we, these two Paulis, they are not general Paulis, they are the Paulis that anti-commute, okay? So the sigma x, sigma z plus sigma z, sigma x is 0, right? So, and then for any Pauli, there is usually a Pauli that anti-commutes with it. And let me just say that there is a kind of general way of grouping Paulis into something that will be unitary. Is this is unitary with under it is sufficient condition. So sufficient conditions, meaning that it's not necessary. There are other ways to build unitary out of Paulis, but the sufficient is that Pn prime, they anti-commute, and the coefficients are real, and they let's say sum with squares to 1. Okay, so this is easy to satisfy by just normalizing coefficients if needed, right? But this part is more essential if you can take the if you can take the Paulis that anti-commute, you can then make a group that is a bigger group that also has a unitary, or it's going to be in this case, unitary that U dagger equals to U, right? Because all the Paulis are like that and the coefficients are real. Yes, so imaginary part of Cn is 0. So how can we see this? Very simply, you just square it. Sorry, you just square it. Cn Pn. And then what you get is essentially diagonal terms. And we know about Paulis that they are identities in diagonal terms, right? And we only gonna get an identity here because the coefficients are satisfying this condition. Plus, there's a off-diagonal part, Pn, Pn prime, Cn, Cn prime. But we will always have, let's say, n prime, and then the other order n prime n, right? So therefore, because of the anti-commutativity, this whole thing, n not equal to n prime, this whole thing is going to be 0 because of the anti-commutativity, right? And so one can, this way, construct bigger unitaries. Now, what we still need to show that our grouping actually benefits the one norm, right? So what is the one norm that we are getting by doing this grouping? General combination of Paulis, even if we find the ones that are anti-commuting, they are not having the coefficients that satisfy this condition, but we could always make it. So if we started with, let's say, the coefficients that are not satisfying this, we gonna do the renormalization. So we're gonna multiply by the coefficient 2 norm, and then that will allow us to divide the coefficients by 2 norm of that vector. Now, this will be our unitary, and this will be the coefficient of that unitary. Okay, and so now the question is, did we win by doing this? Because we got the 2 norm of the coefficient, while here we had 1 norm. 1 norm. So what's the difference? 1 norm is the sum of absolute values, right? So 1 norm of coefficient is sum of Cn absolute values, and the 2 norm is a square root of sum Cn squares, so values. Okay. So which one is bigger, this one or this one? If this one is bigger, then we actually didn't win anything. If this one is bigger, then we won, right? And it's easy to see that with few lines of algebra that this one is always bigger or equal, and it's only equal if there is only one term, then equal. But in general case, this is always bigger than this. Again, the kind of the way to see it, let's just essentially start with this and square it. So if you take the C2 norm and square it, right, then you're gonna get sum over Cn squares. This is the same as squaring Cn 1 norm, squaring and subtracting the all of diagonal terms, okay, which are all positive because we have absolute values here. Okay. So 2 norm squared is equal to 1 norm squared. So you see 1 squared minus something positive. So 1 norm squared, you could bring this there and show that, okay, C1 is always larger than C2. Okay, so we always win by grouping. So the norm, the coefficient we're getting here is always smaller than what we would get if we just leave them grouped. Okay. All right. So, any questions? Okay, so then that's probably all for today, and we'll continue next time discussing how we can actually use this to measure off-diagonal matrix elements. It could be useful for some methods. Okay.